So welcome to the second plenary session of the April meeting. And the title of this session is The Quantum 100 Years Ago, the Quantum Today, and the Quantum Tomorrow. We have three terrific speakers. And the first speaker in this session is John Heilbron from Berkeley, and he's going to talk about Bohr's creation of his quantum atom. John. Excuse me.
Well, good morning. Can you hear me? Yeah. When Niels Bohr sent his revolutionary paper on the hydrogen atom to press 100 years ago, the lions in the field, Lorentz, Planck, Einstein, and a few other theorists had been reading the writing on the wall for some time, graffiti like E=H nu. Like Bohr, they understood that the classical physics they represented so well was inadequate to describe the microworld of atoms and molecules. Unlike him, however, they hoped that the required modifications would not demand the surrender of continuity, causality, and space-time description, which were fundamental to their understanding of their subject. Bohr demanded even these sacrifices. The author of this revolutionary paper was a 27-year-old assistant professor at the University of Copenhagen. Although his reputation scarcely extended beyond the Kattegat, he felt himself the potential equal of Lorentz and the rest, and did not hesitate to correct them. Einstein, who was not a timid physicist, expressed amazement at Bohr's courage. He told their mutual friend, the chemist George Hevesy, that he had once entertained similar notions, but had not had the pluck to follow them up. The odd word pluck, perhaps plucked from a dictionary to convey to the Dane Bohr what the Hungarian Hevesy heard in German from Einstein, perfectly connotes the mix of daring and fortitude, of persistence against the odds, of measured combativeness that Bohr saw in himself. Bohr referred to his pluck as wildness and boiling blood in the letters he wrote to his fiancée Margrethe Nørlund during his postdoctoral year in England in 1911 and 1912. These letters are the new material referred to in the abstract of my talk. There's much in them besides news about the psychological state of a wild man from the north. They also contain many apt and revealing quotations from a wide range of Scandinavian, German, and English literature, and bits of a general philosophy or religion that relate directly to Bohr's physics. Excerpts from this and other family correspondence will be published soon by Finn Oserud, who's director of the Niels Bohr Archive in Copenhagen, together with a new account of Bohr's path to the quantum atom. From this newly available material, it appears that before Bohr invented his atom, he aspired to be, and to be recognized as, the greatest Danish thinker of his time. An example of such a person was Søren Kierkegaard, who dominated the intellectual scene during the days of Bohr's grandparents. In Bohr's opinion, Kierkegaard was the author of one of the very best books ever written by anyone, Stages on Life's Way. In this best of books, Kierkegaard fractured his rich personality into half a dozen lesser characters whose conflicting experiences and opinions are all versions of himself. At least one of Kierkegaard's multiple personae was also a version of Bohr. This character was, as Kierkegaard described him, madly in love with thought, or rather with thinking. No young lover could be more deeply moved than he was by that inexplicable process by which one thought fits into another. Bohr began his revolutionary paper of 1913 by expressing the fundamental postulates defining the stationary states in 4 different and conflicting ways, as if he were writing stages on life's way about electrons. The new material helps explain why Bohr felt the need to begin with a medley of partial and contradictory truths. Before I get there, however, I must describe the situation in physics as Bohr experienced it in 1912. He began his postdoctoral year in Cambridge, hoping to convince the professor of physics there, Joseph John Thompson, that the Cambridge approach to electrons was far too democratic. Bohr had found in his thesis, which was on the electron theory of metals, that he had to impose restrictions on equipartition to explain the behavior of bound electrons. Now, the Cambridge mathematicians knew full well that if equipartition held universally, disaster would ensue for physics anyway, if not for nature. To avoid this catastrophe, the mathematical physicists in Cambridge proposed that the universe has not existed long enough for full democracy to set in. Electrons and ether modes are as reluctant as human beings to share their wealth. Bohr regarded this subterfuge as nonsense and expected to be able to persuade Thompson and Thompson's colleague Joseph Larmor to give it up. This would not seem to have been a promising project for a young man. Here are the two that Bohr intended to persuade to his own views. Joseph John Thompson, then recently knighted for his discovery of the electron and other services to humanity, and Joseph Larmor, the chief of the Cambridge mathematicians, also then recently knighted. Bohr mobilized his courage to deal with them, but to no avail, as neither would be drawn into his problem. Thompson had lost his enthusiasm for the electron theory of metals, and even had he retained it, he would not have had the patience to read Bohr's magisterial thesis in the poor English translation of it that Bohr had to offer. Larmor politely refused to have anything to do with it until it was published in a proper English journal. Consequently, none of the Cambridge mathematicians could take Bohr's measure as a physicist. Despite his disappointment as not being regarded as the equal of a Cambridge mathematician, Bohr liked the place and learned much when there. He extolled Thompson's lectures and rated Larmor's book, Ether and Matter, or as we might phrase it today, Radiation and Electrons, as an inspiration. When I read something like that, he wrote his fiancée, it makes my blood boil with enthusiasm and desire for emulation, not with the irritation that the book's cumbersome English may inspire today. It is a great book, a premature essay in a theory of everything, full of hints and hues for painters of world pictures. Bohr read it 2 or 3 times. In March 1912, he moved to Manchester to learn something about radioactivity from Ernest Rutherford and his collaborators. There he met young men able to appreciate his merit. Hevesy, Charles Galton Darwin, and Henry Moseley all engaged in work in which Rutherford took an active interest. It was not long before Bohr switched his research field from the electron theory of metals to the dominant subject at Manchester, the development of the nuclear atom. Rutherford had revived this model in 1911, not as an embracing atomic theory, but as everybody knows, as an explanation for anomalies in the scattering of alpha particles. Having recovered his confidence in Rutherford's environment, Bohr boldly pushed the nuclear model far beyond scattering theory, far enough to scare Rutherford, who had earlier not hesitated to proclaim the transmutation of the elements. The extrapolations Rutherford judged extravagant included the concepts of isotope and atomic number. According to physics folklore, the doctrine of atomic number, which assigns a single electron to hydrogen, showed immediately that ordinary mechanics could not hold within the atom because the electron would be obliged to radiate away its energy and fall into the nucleus. This difficulty did not play an important part in Bohr's thinking. Since hydrogen atoms exist and don't glow in the dark, the atom builder had to assume that in its natural state, a bound electron can circle a nucleus without radiating. Bohr made this necessary assumption when he took on the nuclear atom and left the problem of radiation as he did that of radioactivity, to the indefinite future. He supposed further that in the ground state, electrons obeyed ordinary mechanics as if they were planets revolving around the sun, at least insofar as their mean motions were concerned. Just before he left Manchester, at the end of 1912 for his wedding in Denmark, Bohr told Rutherford that he had adopted as the quantitative condition defining the permanent state of the atom the rule that the kinetic energy of every electron in the atom must be proportional to the electron's orbital frequency. Apart from this ad hoc restriction, ordinary mechanics held sway in the permanent state, except for perturbations in the plane of the motion, which are not stable. Evidently, the restriction, which Bohr wrote in the form kinetic energy is a constant k times the orbital frequency, this equation was an adaptation to the nuclear atom of the condition that Planck had placed on his radiators or his resonators in his theory of the black body radiation. Bohr told Rutherford that the constant k was some fraction of Planck's h. It is not easy, though it is easily misleading, to adapt Planck's radiation theory to the nuclear atom. That is because Planck's resonators vibrate at the same frequency no matter what their energy, whereas the frequency of orbital motion about a nucleus changes with kinetic energy. At first, this ambiguity was not a problem for Bohr. When he described his postulate or condition for the ground state to Rutherford in July 1912, this being about 5 months before he sent in the paper 1913 for publication, he did not need to distinguish the frequencies with which the electrons circulated from the frequencies of the light an excited atom could emit or absorb. This was because, following Thompson's research program in atomic physics, Bohr did not concern himself with spectra. He still had plenty to think about on his way home to Denmark. Early in 1913, one of Bohr's associates at the University of Copenhagen asked him how his model atom produced spectra. He replied the spectra were too complicated for his methods. The colleague persisted. Have you looked at Balmer's formula? Bohr understood its import immediately. This was owing to the intervention of another Cambridge physicist or mathematician named John William Nicholson. Nicholson had traced spectral lines to oscillations of electrons in a nuclear atom perpendicular to their orbital plane. Assuming that the frequencies of the oscillations of the electrons were the same as the frequencies of the radiation emitted, Nicholson computed the spectra for various simple ring atoms. The results were spectacular. With the radius of the ring as his only free parameter, he matched the output of 2 of his ring atoms with 10 unattributed lines in nebular spectra and 14 lines from the solar corona. The match extended to 3 and even to 4 significant figures. And having fixed the radii of his model atoms, he could calculate the angular momentum of their electrons on purely classical grounds. And in all cases, the momenta came out to be, guess what? Integral multiples of Planck's constant h divided by 2 pi. Bohr easily checked that if he allowed higher circular orbits characterized by some integer n, satisfying the condition that the ratio of kinetic energy to orbital frequency equaled n times 1/2 of h, then his electrons, like Nicholson's, had angular momentum equal to integral multiples of h over 2 pi. This exercise, which took place around Christmas time of 1912, did not produce quantum jumps, however, but an instructive hybrid model in which an electron is captured by a nucleus in stages, dropping from one allowed state to another, in each of which it radiates away energy by oscillating perpendicular to the plane of motion, rather like a pinball falling through a series of stiffer and stiffer tuning forks. The state Bohr considered in his talk with Rutherford would be the last in the procession of allowed states, reached when the captured electron had lost by radiation all the energy it could. This hybrid did not last long. When he interpreted the Balmer formula as an energy equation in the sense of Planck's quantum condition, Bohr jettisoned his compromise with Nicholson and introduced quantum jumps. Taking the running Balmer term to be kinetic energy divided by h, Bohr achieved his famous derivation of the Rydberg constant R. Since this is mother's milk to you, I leave it there for you to satisfy yourself with as I continue. But by doing so, by introducing the quantum jumps, Bohr destroyed the direct connection between the radiator and the radiation, a result immensely off-putting to the classical physicist. Taking the running integer n of the Balmer series to indicate the number of an allowable state counting outwards from the nucleus, Bohr had the bizarre result that the nth Balmer line is the orbital frequency of the second allowed state less 1/2 n times the orbital frequency of the nth state. Or, in other words, the radiated frequency had only an indirect and opaque connection with the mechanical frequency of the electron supposed to be responsible for its production. This is the feature of Bohr's quantum atom that seemed the most extraordinary to himself and to the best informed and most critical of his contemporaries. Rutherford's reaction was particularly instructive. Unable to picture how an electron could stir up the ether without vibrating, he objected that it would have to know where it was going to stop before it started its jump in order to vibrate appropriately during the journey. And how could it know its terminus in advance? Einstein's reaction was once again amazement. When Hevesy told him about experiments that confirmed Bohr's bizarre equations, he was extremely astonished, and he told me, Hevesy, then the frequency of light does not depend at all on the frequency of the electron. This is an enormous achievement. Experimental confirmation of Bohr's theoretical computation of the Rydberg constant extended to 5 significant figures. No one had come close to such precision in deriving the value of any observable from an atomic model. However, the basic postulate that the kinetic energy was n times the orbital frequency times half of a quantum was almost as obscure as its consequence for the Balmer frequencies was bizarre. Bohr would have considered it unprincipled and irresponsible not to ground his postulate in a more general proposition. So, like Planck seeking a theoretical justification for his successful black body radiation, a black body formula, Bohr cast about for a general ground for the postulate. He cast promiscuously. The harvest was 4 different and mutually inconsistent or barely consistent ways of grounding the fundamental postulate. The first 2 developed different analogies to Planck's theory. The third is an adumbration of the correspondence principle, quantitatively at odds with the first 2. And the fourth is the familiar quantization of the angular momentum. The first 3 are conditions on the radiation. The fourth is a rule about the orbit. Bohr soon dropped the first 2 as misleading, took the third as the basis of his subsequent principled derivations, and used the fourth for convenience when discussing circular orbits. I don't have time to describe the constructive inconsistencies outright and outright contradictions among these formulations. It's enough to say that each contains some element of truth, and that Bohr thought that in his first presentation of his theory, he needed them all. Here they are for your contemplation. The practice of holding several formulations simultaneously, despite their uncertain coherence, or regarding the same subject from several different and even contradictory points of view, was habitual with Bohr. It was his way of discovering and exhibiting the truth, or rather the collection of partial truths relevant to the matter in hand. One of his later oracular utterances has it that the opposite of a deep truth is a deep truth, and the opposite of an ordinary truth is clarity. Shortly after arriving at Cambridge, Bohr entertained a party of mathematicians with his notions about the nature of truth. Regrettably, all Niels told Margrethe about the conversation was that no one present had ever heard anything like it before. What Bohr might have told them comes in another letter, which deserves quotation in full. Its context was an apology for a criticism Bohr had made of Thomas Carlyle's On Heroes and Hero Worship, which Margrethe had sent him. She apparently saw some parallels between Carlyle's great men and her fiancé. Here's what Bohr wrote. You ask what I meant by what I wrote about Carlyle. By comparing his style with a sermon, I just mean that one does not demand from a sermon that everything in it should be true, in the same way as from a great work of literature. There exist so many different truths. With a sermon, the main purpose is to show your sympathies and make others enthusiastic about them. And that, of course, can be just as important as trying to create something which one calls greater, that is more universally human, and the truth of which will be of a somewhat different kind, coming close to the so-called scientific truths, which are again of a somewhat different kind. This is so stupidly and badly put, but it is something I feel very strongly about. I can almost call it my religion, that I think that everything that is of any value is true. With this unusual religion in mind, it is easy to see why Bohr took special delight in Kierkegaard's stages on life's way. Kierkegaard needed 4 of his many personae to depict the first or aesthetic stage by means of drunken speeches the 4 of them gave about love, life, and the universe. Each says something true, though his statement conflicts with what the others say. The second stage is married life. A good and proper marriage is perfect and complete. This is not quite feminist doctrine now. The wife's to be patient, understanding, supportive, protective, enabling the husband to reach the highest level his talents and training permit. Neither party can achieve as much apart as they can by pooling their complementary qualities. Each contributes an equal share to the truth of married life. Bohr needed such a partner more than most men. The third and final stage of Kierkegaard's stages, the religious, can be reached only by a leap of faith, a quantum jump that Bohr did not make. Rather, as will appear in a minute, he leapt in the opposite direction. Niels made clear to Margrethe the sort of mate he needed by means of leading questions and literary references. Will you fly with me to Iceland, he asks, and if my work requires me to leave you there, will you wait for me? To this odd question, she gave an answer in the usual style of their communications. Yes, Niels, I'll wait for you, as Solveig did for Peer Gynt. This was perhaps to offer more than was needed, since Solveig spent her entire adult life patiently expecting the irresponsible Peer to return from his escapades. A better role model was the quiet, intelligent, dependable Agnes, who made a man of the eponymous hero of David Copperfield. Bohr sent Margrethe his copy of Copperfield in English immediately after he had finished it. She no doubt knew it already in Danish, for Dickens in translation was a favorite with the Bohr family. Bohr's mother knew the entire Dickensian canon and knew how to exploit it. In a moment of doubt, Margrethe had worried that she might not have been created for the role of a complement to Niels in a perfect Kierkegaardian marriage, and considered completing her training to be a school teacher. Her mother-in-law-elect brought a squadron of Dickens heroines to the rescue. You are another Agnes, Biddy, Florence, Little Dorrit, she said, referring to David Copperfield, Great Expectations, Dombey and Son, and Little Dorrit, all of which she expected Margrethe to know. Only you are better than all of them, since you are real and love our little Niels. Margrethe wanted to return to school to qualify to teach, and also to learn enough to live with a compulsive intellectual. Mrs. Bohr dismissed the suggestion. You do not have to know a lot, she replied. The essential point was to understand and appreciate the value of intellectual work. She went on as if she were a college president approaching a reluctant donor. Intellectual work is so rarely valued because so few know what it requires of strength, diligence, and unselfish striving, but you and I know it. She finished with a request for Margrethe's gift of a lifetime. You understand, our dear boy, your soul is in harmony with his. You will never lose courage, even if the world does not always recognize what a rare treasure Niels is. Well, Margrethe agreed to be Agnes, Solveig, and the lot. In Bohr's version of the truth of marriage, hers would be a coordinate, not a subordinate role. And for a time, she was a collaborator as well as a helpmate, acting as sounding board and amanuensis, as the hands as well as the heart of their joint enterprise. It was a curious feature of Bohr's creativity that he needed an interlocutor as he worked, especially when writing up his results. Chief among Margrethe's tasks after her marriage was to pay Niels' debts. He expressed this expectation over and over again. The payment was to be drawn on her great soul, not her bank account. Niels never had financial worries. The debts were the obligations he supposed he owed to his family, teachers, and friends who believed in his greatness and encouraged him to develop his abilities. The recurrence of this theme suggests that casual observers might have thought Niels incompetent and dull. A story from his boyhood illustrates this possibility. He and his Aunt Hannah, who incidentally had a master's degree in physics and founded the first coeducational school in Denmark, were riding in a streetcar. Niels was following some tale his aunt was telling so intently and with a face so devoid of expression that a woman seated opposite felt impelled to express her sympathy with Hannah for having an idiot for a child. Bohr's father, whom he and Margrethe idolized, was the professor of physiology at the University of Copenhagen. He liked to say, "I am silver, Niels is gold." He referred to medals awarded by the Danish Academy of Sciences. He had won a silver one earlier in his career, and Niels a gold one. His subject was a theoretical and experimental treatment of the physics of water jets, that is, Niels' subject. This prize and the publication by the Royal Society of London of the results that won it not only did not discharge the debts Bohr owed his supporters, but substantially increased them. He had mobilized family and friends in his researches. He did the experimental work in his father's laboratory with the help of its mechanics. His father helped compile the tables of results. His brother and his future brother-in-law worked at the calculations. His mother acted as amanuensis. Niels provided the main theoretical ideas and the experimental setup, but the credit of working up the results that brought Niels his gold medal belonged to the nuclear Bohr family. The only way to discharge the growing debt was by overachievement. Niels believed that only with Margrethe's support and constancy could he smooth out his mood swings and prove his true value. When the Cambridge mathematical physicists underestimated him, his need for an Agnes intensified. Mrs. Bohr had put her finger on the most important quality Niels' Agnes must have. She must hold high and subjugate herself to the value of intellectual work. Niels must have time to think in a loving and supportive environment. Like Aristotle's unmoved mover, Bohr's essence was thinking. He said as much when explaining to Margrethe how he came to lose his religious faith. He had tried hard to believe in salvation, the salvation of his little soul, and to understand what that might mean, but he had lost the struggle and realized suddenly and with complete conviction that Christian dogma was not true in any of the many senses of truth. When he confessed this leap into non-faith to his atheist father, he received a sage smile in reply. "That smile, my little one," he wrote Margrethe, "told me a lot. My courage roared so wildly, wildly, for I knew then that I, too, could think." This is a golden text. The approving smile of the man he most admired in the world taught him that he belonged among the few who could reason their way free from the standard beliefs of their class and culture, place and time. He would repeat the performance when recognizing that ordinary mechanics represented the truth of the microworld no better than conventional religious beliefs accorded with the meaning of life. In the fall of 1912, Niels and Margrethe, now married, began in their complementary ways to warm the nest egg that Niels had brought from Manchester, or to speak plainly, to develop the rough quantum atom he had discussed with Rutherford. Back in the familiar, nurturing Danish cultural environment, as inspired by Rutherford's interest in his work, yet another debt, Bohr managed to hold simultaneously to the various bits of truth contained in classical mechanics as applied to the microworld, the nuclear model, Planck's quantum theory, Nicholson's spectral theory, and his own quantum atom. The inconsistency among these truths appear in the 4 different conditions Bohr imposed on his atom in order to derive the Balmer formula. Gradually, he diminished the number of partial truths to a complementary pair. Classical mechanics is applied to electron orbits, and the quantum condition E equals h nu applied to the radiation, or in more colorful language, to stationary states and quantum jumps. Bohr knew perfectly well that these concepts were at best crude sketches of features that would figure in a proper picture of the microworld. The disjunction between radiated and orbital frequencies showed clearly enough that the electron orbit was primarily a calculating device, which, however, could still hint at the way forward to anyone who could decipher the limited truths it expressed. For a decade and more, Bohr led his ever-enlarging band of atomic cryptologists. He managed to tease out information about the intensities and polarities of spectral lines, which explained most ad hoc selection rules. He worked out the structure and populations of electronic shells, which eventuated in the discovery of hafnium. He tried to connect the orbital frequencies with the probabilities of electron jumps and ended in a super courageous violation of the principle of energy conservation. And he established the line of march that led to matrix mechanics, the Pauli principle, and complementarity. Quantum physics taught Bohr that physicists can only give an adequate description of all the phenomena presented in experiments if they use complementary concepts, like wave and particle, to refer to the same underlying reality. The challenge was to limit the use of each member of such a pair so as to avoid the contradictions inherent in them. He continued to think in complementary dichotomies when, in the 1930s, he expanded the lessons of quantum physics to include the wider questions that had interested him even before he knew that he could think. His experience with physics caused him to reduce the multiple truths of things to complementary pairs, wave and particle, space-time and causality, but also free will and determinism, mechanism and vitalism, yin and yang. Without knowing much about Bohr's mental furniture or his remarkable way of arranging it, Einstein understood that Bohr's genius was altogether unique. 2 letters published in the last volume of the Einstein papers, edited by Diana Buchwald and her colleagues at Caltech, illustrate the point. In one letter, Einstein discouraged a correspondent from disturbing Bohr with a question. Bohr was then overworked from planning his Institute for Theoretical Physics in Copenhagen and from thinking in general. Einstein counseled that physicists should do everything they could to protect the great asset that was Bohr's mind. In the second letter, he says why they should do so. "It is most remarkable," Einstein wrote, "that any such mind should exist at all." Thank you.
Thank you, John, for a beautiful talk. We have time for a couple of questions. If there are any, there are microphones in the aisles. So if you have a question, please go to the microphone. It's very hard to see.
Exactly my problem.
Virginia doesn't need a microphone.
No.
Okay, I hear Virginia tremble, and she's right. She doesn't need a microphone.
Is Nicholson the same Nicholson who talked about abundances of the elements in stars in about the same time frame?
No, this is, it's not George, it's John William Nicholson.
Okay, well,
Yes, it's John. He may have done.
well, either there were 2 Nicholsons in Cambridge or it's the same guy.
Okay, then it's the same guy. 2 Nichols in Cambridge.
Is there another question?
Yes. Right here.
Oh, at the microphone. I can't see you, so go ahead. I heard your voice. Ask your question.
When we look back at theories such as this one, or even special relativity,
I'm
for
sorry,
example,
we can't hear you. If you could
when we
speak.
look back at theories such as this one, or even special relativity, for example, it is often imagined that they were immediately and instantly accepted as being obvious. in real life, what was the initial reception of Bohr's ideas, and what was the lag between his first publication and their general acceptance by the community?
The discovery of the untangling of the spectra of hydrogen and ionized helium came quite quickly, and that was a great plus for the theory. The other indications that Bohr was on the right track, for example, the discovery of the Stark effect, also came in 1913, 1914. The Frank and Hertz experiments, misinterpreted by them, were already in hand and so on. But there were few people who were persuaded by him before the First World War. So there's the hiatus owing to the war, during which Sommerfeld and his school were still at work because Sommerfeld was too old to serve in the military. And they transformed the theory in the way you all know, by introducing the phase integrals and applying them. Sommerfeld wrote a great textbook on all this, which was published in 1919. And when people demobilized, there was only one game in town for atomic physicists, and that was the Bohr theory as represented by Sommerfeld. And everybody had to learn German, the language of the defeated enemy, in order to be able to re-enter the field.
Thank you, sir.
So thank you very much, John, for a beautiful talk.
Thank you. And is this your computer? Okay, good.